In this video, I'm going to walk you through how to do the bonding and structural formulas practice test. So problem number 1, it asks you to draw Lewis structures for CSE2. So the first thing is, since we only have one carbon, we're going to put carbon in the middle, and then we're going to put in our 2 seleniums. Then we need to add up valence electrons. Carbon is in group 14. So it has 4. Selenium is in group 16, so it has 6. So 6 plus 4 plus 6 is 16 electrons, or 8 pairs of electrons. So then we have to distribute the electrons around. We put 1 pair between the carbon and each of our seleniums, so that's 2 of our pairs. Then we're going to place the other pairs around. Now we're going to save carbon for last. So our goal is to get everything to have 4 pairs of electrons. But at this point, we are now out of electrons. Because once we draw 1, 2, 3, 4, 5, 6, 7, 8 pairs of electrons, that's all the pairs we have. But carbon only has 2 pairs of electrons, and it needs 4 pairs. So what we're going to have to do is make some double bonds. So we're going to take one of these pairs off of selenium and share it with carbon, and then we're going to take another pair off the other selenium and share it with carbon. And because we can make 2 double bonds instead of a triple bond, that's always preferable. You don't want to make triple bonds unless you don't have a choice. Then it says identify the shape of the molecule. Well, since we only have 2 things attached to this carbon, and these electrons repel each other, they're going to get as far away from each other as possible, which is opposite sides. So the shape is going to be linear. Now, when we identify the strongest intermolecular force, the strongest is hydrogen bonding. If there's no hydrogen in here, there's clearly no hydrogen bonding. The next would be dipole-dipole. Now, because this molecule is linear and it's nice and symmetrical looking, it's not going to be dipole-dipole. It's not an uneven distribution of charge. So that leaves us with the last option, which is dispersion forces, or London dispersion forces, depending on what you'd rather call them, or you can just call them London forces. And number 2, NH3. We draw our nitrogen and our 3 hydrogens. We add up the electrons. Each hydrogen has 1 and nitrogen has 5, so 1 plus 1 plus 1 plus 5 is 8 electrons, or 4 pairs of electrons. So we go 1, 2, 3, and then keep in mind you never add anything else to hydrogen. It's the exception to the rule. This 1 pair of electrons is all hydrogen wants. So our 4th pair we're going to put on the nitrogen, because it needs to have 4 pairs of electrons, or 8. That's why it's called the octet rule. 8 electrons. 2, 4, 6, 7, 8. This molecule, you have 3 things attached to the central atom, so it's going to be trigonal something. Now, if it did not have this lone pair of electrons, it will be trigonal planar. It will be flat with 120 degrees between each of these. But this extra pair of electrons is going to push those other 3 hydrogens down, and that's going to make this trigonal pyramidal. And for intermolecular forces, in this case we have hydrogen attached to nitrogen. Keep in mind, if hydrogen is attached to fluorine, oxygen, or nitrogen, you have hydrogen bonding. And number 3, we're drawing the SO3 -2. That's our sulfite polyatomic ion. So sulfur, oxygen, oxygen, oxygen. We add up our electrons. 6 plus 6 plus 6 plus 6 is 24. But this -2 charge means we add 2 more electrons. So we have 26 electrons, or 13 pairs of electrons. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then the last thing we need to do is put this in some square brackets and give it a -2 charge. Just like in the previous case, This is going to be trigonal pyramidal. Now this does not have hydrogen bonding because there's no hydrogen in there. What this is, however, is this is a polar molecule because it's asymmetrical. This trigonal pyramidal shape, it's essentially got these electrons sitting on top, pushing the oxygens down, making the whole shape asymmetrical. So this is a polar molecule, so it has dipole forces. In number 4, we have carbonate, CO3, with a -2 charge. So we have 6 plus 6 plus 6 plus 4, that's 22 electrons, plus 2 more for the -2 charge, that's 24 electrons, or 12 pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, if we look at this, carbon is still short a pair of electrons, so it needs to borrow from one of these oxygens. This is the part a lot of you really don't like, but because we could borrow from any one of these oxygens, like say this one, to make a double bond, since we could make the double bond here or there, we need to draw all 3 possibilities. We need to put these in square brackets with arrows in between them, and we need to put the -2 charge on there. And then for the shape, this is going to be trigonal because it's got 3 things attached to the central atom, and it's going to be flat, so trigonal planar. And this molecule does not have hydrogen bonding. Trigonal planar molecules are generally not asymmetrical, so this is not going to be polar. So all this is going to have is dispersion forces. And we're done. Number 5. The nitrite ion. Nitrogen, oxygen, oxygen. We have 6 plus 5 plus 6, which is 17 electrons, plus 1 more for the -1 charge. So 18 electrons are 9 pairs. 1, 2, 3, 4, 5, 6, 7, 8. And once again, always save the atom in the middle for last, but we put the 9th pair there. Now this nitrogen is short a pair of electrons. So it can borrow a pair from either one of these oxygens. So it could borrow from this oxygen over here and make a double bond, or it could borrow from the oxygen on the left side and make a double bond. So put some square brackets and our arrows for the resonance structure. We'll also add the -1 charge. Now this molecule, once again, with 2 atoms attached, they would try to get as far apart from each other as possible and be linear. But this other pair of electrons in here is going to push those 2 oxygens away from each other, kind of push them down a little bit into kind of a V shape, and we call that bent. And bent molecules are polar. This doesn't have hydrogen bonding, obviously, so this has dipole forces. Number 6, we have the ozone molecule, or O3. The O, when we add up the electrons, we have 6 plus 6 plus 6, which is 18, or 9 pairs. 1, 2, 3, 4, 5. This is going to look exactly like the previous one. 6, 7. If you put another pair of electrons down there and one on oxygen, we're short, so we need to make a double bond. So we could borrow from that oxygen, or we could borrow from the oxygen on the right. We'll put some brackets in there and put some arrows in between. This is also bent, And it's also going to therefore be polar and be dipole, dipole. Number 7, SO2. 6 plus 6 plus 6, 18 electrons. Oh my goodness, this is going to look exactly like these previous two. So let's just kind of draw that out since we know this. Don't expect me to give you a whole bunch that are almost exactly the same on your test. Once again, this is going to be bent and dipole-dipole. Number 8, the H2S. You have 1 plus 1 plus 6, or 8 electrons. Divide that by 2, that's 4 pairs of electrons. So we go 1, 2. Keep in mind with hydrogen, we do not add any more electrons to hydrogens, so our other 2 pairs just go on the sulfur. Now this shape, although it may look nice and linear the way we drew it, these electron pairs are going to kind of push those hydrogens away from it and make this molecule bent. Now, even though we have hydrogen in this molecule, there is no hydrogen bonding because hydrogen is not attached to nitrogen, oxygen, or fluorine. It's attached to sulfur. Now, this molecule is still polar, so it's dipole, dipole. Also, because it's bent, a lot of times you'll see this molecule drawn like this to kind of show that it's bent. Although really it's not a 90 degree or 180 degree angle. The angle in there was 109.5. Number 9, carbon tetrabromide. Each bromine has 7 electrons, so that's 28 plus 4 for carbon is 32 electrons, or 16 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Looks like we're done. This thing with 4 things attached to the atom in the middle is tetrahedral. And this is completely symmetrical. There's no hydrogen bonding. It's not polar, so this is just dispersion forces. Number 10. Hydrogen fluoride or hydrofluoric acid. We have an H and an F. We have 1 plus 7 electrons, or 8. That's 4 pairs. There's our first pair. We don't put anything else on hydrogen. Do not make a double bond. Do not put anything else on hydrogen. We'll put the other 3 pairs on the fluorine. If you only have 2 elements in a compound, it must be linear. And since we have hydrogen bonded to a fluorine, this is hydrogen bonding. One thing I do want to point out is that the hydrogen bonding is not this bond right here. It's if you have one HF molecule where this end of the molecule is going to be somewhat negatively charged and this end somewhat positively because fluorine pulls those electrons towards itself. If you have another HF molecule, it's got the same thing going on. The hydrogen bond is where the hydrogen in this molecule is attracted to the fluorine in that molecule. So this is our hydrogen bond. So back to number 11. N2, we have 2 nitrogens. Each nitrogen has 5 electrons, so that's 10 electrons or 5 pairs. So if you try putting the electrons in, there's 1, 2, 3, 4, 5 pairs of electrons. That leaves this nitrogen short 2 pairs of electrons, so we need to borrow a pair, make a double bond. We need to borrow another pair, make it a triple bond. That's what it looks like. If you want to make it all nice and symmetrical, you can put those electrons over there, since they would be repelled by those. You don't have to do that if you don't feel like it. But this molecule with 2 atoms in it is linear. And 2 nitrogens will perfectly equally share their electrons, making this nonpolar, and so this is dispersion forces. Last but not least, we have number 12 with the chlorate polyatomic ion. We've got chlorine and 3 oxygens. So we have 6 plus 6 plus 6, which is 18, plus 7, 25, negative charge 26 electrons, or 13 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 pairs of electrons, put a negative 1 charge on it. This molecule, because of that extra pair of electrons on there, it is trigonal pyramidal. This molecule would be polar as a result and be dipole dipole. Keep in mind, key way to remember this when you're trying to figure out the intermolecular forces is if it has hydrogen attached to nitrogen, oxygen, or fluorine, it's hydrogen bonding. If the molecule is bent or it's trigonal pyramid, it's going to be dipole-dipole. Will be the strongest intermolecular force. And everything has dispersion forces. So if you have hydrogen bonding, you're also going to be polar and have dipole-dipole and dispersion forces. If you have dipole-dipole, you also have dispersion forces because everything has dispersion forces, but this is the strongest. Dispersion is the weakest. Now, for the matching, a characteristic of all polar molecules is that they have dipole-dipole forces. The strongest intermolecular force is hydrogen bonding. If I'd asked what intermolecular force is found in every molecule, between every molecule, that would be dispersion forces. Once again, hydrogen bonding only occurs when a hydrogen is connected to a fluorine, oxygen, or nitrogen. As you move from left to right across a period, the electronegativity, it generally increases all the way up to group 17, because keep in mind, the noble gases, they don't have electronegativities. Generally speaking, they don't make chemical bonds, so we don't have to worry about them. Fluorine is your most electronegative element in chemical bonds. It's like playing tug of war, like in this HF. If it's playing tug of war with hydrogen for these electrons, fluorine pulls these electrons pretty close to itself, leaving hydrogen just kind of hanging off on the end there. And so hydrogen, with its only electron, because it only has one, it's being pulled pretty closely to the fluorine, making this side of the molecule pretty negative and this side pretty positive. And VSEPR is how that's pronounced, as an acronym for valence shell electron pair repulsion theory. All right, that should do it.